Hello and welcome. I'm Siyuan from USC. In the next few minutes, we will be exploring the SCEC 2024 meeting poster, number 4, Isotropic High-Frequency Radiation in the Near-Fault Seismic Data, which was recently published in GRL as well. This work was inspired by a seminar given by Rob Graves at USC. They found that at those near-fault stations during the 1979 Imperial Valley earthquake, the fault normal motion was clearly greater than that of the fault parallel at low frequency and became similar after a transition frequency of about 0.5 Hz. Similar observations have been reported by Franco in Chi-Chi and Northridge earthquakes. These observed transitions can generally reflect a combination of source processes that are dominant in different frequency ranges, consistent with a double couple radiation pattern at the low frequency range and the transition to a more isotropic radiation at the higher frequencies. This transition was also observed by Trackman et al. In 2021 for a small earthquake. In the present work, we aimed to improve the constraints on seismic radiation from earthquake sources. To reduce the path effects that increase with distance from the source, we analyzed the near-fault data by 7 magnitude equal to or greater than 6 earthquakes. We chose strike-slip earthquakes with clear overall double couple mechanisms and at least 3 near-fault stations satisfying the geometry demonstrated here. I will skip the following analyzing details. Please come checking our poster or read our paper for details. This figure shows the data and analysis for the 1979 Imperial Valley earthquake, duplicating closely the results of Graves and Pitarca 2016. The fault normal over fault parallel ratios at these individual sites are shown by gray lines here. Their median is represented by the red line. This black dashed line signifies the lowest reliable frequency, and this one is the transition frequency we picked. The second row plots the velocity recordings at 3 stations where the red fault normal components are clearly greater than the blue fault parallel components. Their Fourier amplitude spectra are shown in the next line. The red ones are above the blue ones only at low frequencies. Note that this earthquake was propagating to the northwest, but the AGR station at its backward shows clearly high FNFP ratios at low frequencies, indicating that rupture directivity may not be the dominant factor of these high ratios. The results of 6 other earthquakes are shown here. The frequency dependence of FNFP ratios is still observable at most individual sites. Different events exhibit various amplifications of low frequency FN peak values, this value, and the various transition frequencies. Some events likely have segmentation, local variations of rake and dip, and other source complexities that affect the observations. For the 2016 Uto earthquake, the dense deployment of network enables us to further examine FNFP ratios at sites with various azimuths to the rupture strike. In the 2 quadrants from the fault strike, this one and this one, the FNFP ratios are clearly high at low frequencies, similar to that observed for the earthquakes with closer recordings. In the other 2 quadrants, the FNFP ratios are reversed with similar absolute amplitudes to those in the left 2 panels. This means that if you pick the other nodal plane as the fault strike in this direction, you will observe high FNFP ratios in these 2 quadrants as well. The independence of the fault strike is not consistent with directivity, but a clear feature of the radiation pattern. In short, we provided more constraints on seismic radiation from earthquake sources. Our results likely reflect earthquake source characteristics dominant at different frequency ranges. We indicate by more observations that rupture directivity does not have dominant effect on the results. We suggest that similar FN and FP motions above a transition frequency reflect small-scale tensile faulting and isotropic high-frequency waves near the earthquake rupture zones. We also list here several possible things worth doing in the future, and you can scan this to read our full paper. And welcome to contact us if you have any questions. Thank you.